It's a very long differentiation protocol. It's the longest one I know of. I've never read of another differentiation protocol that is as long as that. I think that alone is one of the reasons for the high purity. And I'm not going to go over the basic science, but we committed these cells to neural progenitor type by re-engineering the retinoic acid regime. Without that re-engineering, we could not get high purity. And then de novo developing a differentiation protocol for high purity oligodendrocyte development. In our hands, in low population numbers, it's about 98% pure. That's the highest purity population of anything that's ever been derived from any stem cell population without the use of FACS sorting, commercial viability. FACS sorting is not commercially viable. We can't take a cubic meter of tissue to get a pint glass or a cup. We need 1 cubic meter of tissue to generate 11 cubic meters of product. It has to be the other way around. This is a positive selection method in which the things that are not oligodendrocytes just don't form or die off along the way. And here's just the last thing I'm going to talk about this, because this is all published and I'd like to move on to newer work, but just a summary video of this. When you get onto 60 Minutes, you can coax them to spend a lot of money on videos, so that's what I did. And this animal has its tail down. It has a lack of consistent coordination front to back, lack of consistent plantar placement. It drags its belly. That's because we have induced a spinal cord injury in the animal that mirrors the majority of human injuries in that it spares some tissue along the outside. And if you imagine that these are your brain or brain stem or corticospinal neurons whipping down your spinal cord, they conduct electricity because they are wrapped in green myelin. And when that myelin is lost in the vicinity of spinal cord injury, several studies have shown that it interrupts saltatory conduction. And so that's why we took embryonic stem cells, made them into an inexhaustible source of human oligodendrocytes in order to address that deficit. So it's literally patching up what's still left after the injury. And we have shown that it reinvests the myelin, that it restores conductivity, and the ability of the animal to locomote is restored. We have consistent 100% plantar placement, front to back, side to side coordination, and weight support. So it was a tremendous degree of recovery. It's worth noting that we induced a level of injury that was just under that degree, so that we could see and detect the outcome. We were able to do that in an experimental manner such that it would facilitate our outcome measures. We don't have that luxury with human populations, of course. We've since moved on. This is unpublished preliminary data for the translation of this type of technology to the clinic. For those of you who don't know that oligodendrocyte story I developed and licensed to Geron Corporation's probably going to enter the clinic very soon. So says Geron. They announced quite recently, about 3 weeks ago, that they anticipate their IND in the spring or summer of this year, and will begin a clinical trial shortly thereafter, which should be the world's first human embryonic stem cell clinical trial under a regulatory body. And the motor neuron progenitor study is likely going to enter type 1 infantile spinal muscular atrophy sometime quite soon. Type 1 infantile spinal muscular atrophy is a genetic disorder that babies have. It kills their motor neurons, and they have, it's an infant mortality is 100%. They all die, and usually within the first year of life. They manifest at 3 months, and usually all die within a year. Now with intubation, you can keep them alive for a little bit longer, but it's a terrible disease. But it is a simple, clean motor neuron loss. It's a genetic defect that, of course, our transplanted cells will not have. Functional outcome measures are very well defined. It's EMG activity, swimming, that type of thing. And the patient recruitment is extremely easy, 100% mortality, and it's a pediatric disorder. And in addition, because these humans only live for a short period of time after diagnosis, the duration of the clinical trial is also extremely short. So for all those reasons, it's a very strategic population to go into. And of course, that's secondary to the compassionate reasons of actually treating this human condition. But it's a wonderful stepping stone to spinal cord injury or ALS. So those two treatments are clinical bound, and they're actually quite marching along quite well. So this is the list that I put together of what I consider a lot of the challenges that I've learned along the way, sitting at the FDA and talking to them, or to regulatory quality assurance officers or teams of focus group meetings, some 100 that I've attended. And let me just run through them one at a time. I think first and foremost is this idea of repeating the experimental findings of others. I think it's absolutely critical. There's sort of two general ways of looking at this. One is a true repetition. The pros of that are it's very ideal. It's exactly what you'd like to do, a true 100% repetition. It's very ethical with respect to the humans because we are going to be putting these things into humans, so you'd want to do that. And risk and efficacy is assessed. The cons are it's extraordinarily costly. It's actually, as Naomi pointed out in her talk, it's very, very difficult. Of the 8 that the NIH has sponsored, not one has worked. And it's not because the people who invented those things and reported on them made it up. It's because it's very, very hard to do a repetition study. And there's a lack of PI motivation generally. There's a lot of reasons why they're difficult to do. The literature support, like I mentioned in the oligodendrocyte story, it really speaks to the robustness. If you can get to the same conclusion using several different populations, then it gives us a feeling of robustness. I actually think that should be strongly valued. It's very ethical, of course, with respect to decreasing animals in experimentation. And that's something that we shouldn't lose track of. Risk and efficacy is certainly not assessed. You can't get it. Because if Scott does something incredibly well in his hands and I use a different cell population and a different injury model and we both get to remyelination and functional recovery, my study does not validate his and his does not validate mine. It would be a stretch to say otherwise. The general feeling might be good, but it is certainly not a repetition. And of course, this is not ethical with respect to humans to have a simply literature support. So this type of analysis, as I pointed out earlier, general literature support, is really insufficient. It does not hit the mark of a true repetition. But I think we should never go forward without it. Safety. This is a real barrier to clinical translation. There's a few things here. One is the injection paradigm itself. How are you going to deliver these things? I forget how much Mackay Sims, how many injection sites he had in his. Yeah, it was a tremendous number of needle pokes into an injured spinal cord. 40 some odd injection sites. So the route of delivery is a major concern for safety. How do you mirror that in a rodent population? Smaller needles, smaller critter, different immune response. And the survival of the cells. I think, honestly, it's the unspoken evil of transplantation biology that 90% of anything you put in dies. If you talk to anybody who's been in the transplant field a long time, they will all tell you that about 90% of whatever you put in whatever conditions, immunosuppression or otherwise, dies post-transplant. That means your transplant volume has to be extremely high. It means your tissue displacement and immune reactions are going to be larger. If we can find a way of increasing the cells in their ability to survive, we can decrease that risk. It's not to say that that risk is not acceptable. In many cases, I think it is. But it is a risk. So one of the directions of my laboratory is trying to do that. We're working with several ketone body type experiments in order to increase the survival of the cells post-transplant. Injection site safety, as I showed you, very critical experiments to do. Immunosuppression is a real concern for clinical translation. These two approaches that I just showed you are both going to require lifelong immunosuppression. There's going to be natural attrition, and that's actually built into the clinical synopsis, where patients think they're getting better if it works, and just stop taking the immunosuppression. Well, when that happened with fetal Parkinson's and Huntington's transplants, a lot of people kept their grafts. Some people rejected them. So it's an unknown at this point. The mortality and morbidity that is associated with immunosuppression is a real concern. The medical community tells me that morbidity can be dissociated from morbidity associated with the treatment. It's quite classic. It's been studied for a great long time, the effects of immunosuppression. But nonetheless, is it an acceptable risk? That's for the MDs and the patients to decide. And this is a tremendous hurdle, one that I came to love and hate. For example, with the motor neuron treatment, it took us 8 months of design with 4 different people making $500 an hour,